Welcome to This Explainer. You know, whenever you look up at a massive skyscraper or drive across one of those colossal suspension bridges, do you ever stop and wonder how it actually stays standing? I mean, against all the forces of nature. Well, today we're going to demystify exactly how these awe-inspiring structures stay up. We're going to zoom way, way down to the microscopic level and then pull all the way back out. We are uncovering the secret life of structural steel. Here's what we're covering today. First, the magic of steel. Second, microscopic muscle, steel's metallurgy. Third, testing the limits. Fourth, the limit state method. And finally, engineering safety. Let's get right into it. Section 1. The magic of steel. Every single grand structure you see starts with a crucial collaboration. Think of it as the trinity of construction. It begins with an architect, right? They design the layout for aesthetics and function. Then, that plan goes straight to a structural engineer, who mathematically calculates the safety and integrity. Finally, the contractor steps in to physically build the thing. Now, if this team coordinates perfectly, we get safe, beautiful, and economical buildings. But what material is this trinity overwhelmingly relying on? It's steel, for sure. And it's pretty obvious why engineers choose it over almost anything else when you look at the stats. Steel has roughly 10 times the strength of concrete. 10 times. Its incredible strength-to-weight ratio is literally the exact reason we can build those towering, slender skyscrapers without them just collapsing under their own weight. Plus, it has this absolutely vital property called ductility. That means it can stretch and bend without immediately snapping, which lets it absorb severe shocks like earthquakes. Throw in the fact that it allows for super fast construction, it's fully recyclable, and has a highly economical life cycle cost. Yeah, it's basically the perfect building block. Section 2. Microscopic muscle, steel's metallurgy. Okay, so the foundation of this entire material actually rests on an incredibly simple recipe. It's just iron mixed with a tiny, tiny amount of carbon. So the crucial point to remember here is that steel's crazy power is entirely rooted in a microscopic physical disruption. See, the carbon atoms are actually smaller than the spaces between the iron atoms. So as they sneak in and dissolve into the iron's natural crystal structure, they physically distort it. And this distortion mechanically blocks the crystal lattices from sliding past each other when force is applied. That atomic level roadblock, that is exactly what we experience as immense mechanical strength. Now, don't let all the lines and curves of the iron-carbon phase diagram intimidate you. Honestly, think of it more like a metallurgical treasure map. It shows us exactly how the internal structure of iron transforms as we add different amounts of carbon and mess with the temperature. For structural steel, we're typically looking at very low carbon levels, usually somewhere between 0.12 and 0.25%. But the real magic, that happens as this extremely hot metal cools down. Let's actually watch that cooling process. Up at around 900 degrees Celsius, our low-carbon steel is hanging out in a phase called austenite. Now, as it begins to slowly cool down in a furnace, a transformation kicks off. Soft, virtually pure iron, which we call ferrite, starts nucleating or forming right around the boundaries of those high-temperature austenite grains. It's really cool. You can basically see the little clusters of ferrite just grabbing hold at the edges. So let's see how this builds. By the time the steel fully cools all the way down to room temperature, the remaining austenite undergoes a massive change. It transforms into something called pearlite. Pearlite is this stunning, tough, striped mixture of soft ferrite and hard iron carbide. And it's this exact lamellar or layered structure that provides the actual mechanical muscle and everyday strength in the structural steel holding up our cities right now. But here's the catch. The speed of that cooling process changes absolutely everything. You can think of cooling rates as a sort of Goldilocks scenario. If you cool the steel very slowly in a furnace, a process we call annealing, the carbon atoms have plenty of time to shuffle around and form large crystals. That gives you a softer, highly ductile steel. On the totally opposite end, if you cool it violently fast by quenching it in cold water, you trap the carbon right in place. That forms martensite. It's an immensely hard but very brittle structure, which is honestly terrible for welding. But if you cool it just right, simply out in the air, you get normalized steel. That's the perfect fine-grained balance of strength and ductility we need for construction. Now, beyond just carbon, engineers rely on a secret recipe of other alloying elements to get things just right. Throwing in a little pinch of manganese, for example, refines the grain size and gives a nice boost to toughness. If you add at least 11% chromium, you magically create a passive, self-repairing shield against corrosion. Bam! You've transformed standard steel into stainless steel. And elements like molybdenum and nickel, they're used to really fine-tune the metals so it perfectly meets the heavy demands of modern structural design. Section 3. Testing the limits. Okay, so we have our metal, but to map out exactly how much stress the steel can actually handle, engineers have to run it through some rigorous trials. The most fundamental of these is the tensile test. They'll take a precisely machined standard tensile test specimen, anchor it firmly by its thicker ends, and then just forcefully, relentlessly pull it apart. Doing this allows them to plot an exact stress-strain curve, which shows exactly how the metal behaves as the force increases. Let's walk through this high-stakes physical journey. First, as the steel is pulled, it stretches elastically, meaning if you let go, it snaps right back to its original shape. But pull a bit harder and you hit the yield plateau, which is where the metal begins to permanently stretch and deform. Curiously, though, it doesn't just fail right away. It enters a phase called strain hardening, where the internal crystals actually reorient themselves, temporarily increasing the metal's capacity to hold the load. Finally, the absolute limit is reached and the specimen fractures, famously breaking into a distinct, ductile cup and cone shape. Beyond just pulling things apart, engineers also have to test hardness, which is the material's ability to resist surface scratching and denting. To do this, testers literally force an indenter right into the metal's surface under a very specific load. The Brinell method uses a tough steel ball for this, while the Vickers method drives a square-based diamond pyramid into the metal. Ouch, right? By measuring the mathematical dimensions of the crater left behind, they can calculate a precise hardness number. Section 4. The limit state method. Now, for a long time, engineers used something called the working stress method. But in the late 1970s, they realized it had some pretty serious shortcomings, and the global engineering community totally revolutionized their approach. They adopted the limit state method. This is a modern, highly sophisticated probabilistic philosophy. Instead of just guessing a safe operating range, the limit state method mathematically guarantees that the probability of day-to-day operating conditions ever reaching the material's failure point is reduced to almost zero. It's a real game changer. In this method, we really need to contrast two fundamental states of the structure. First, we have the limit state of strength, which is also known as collapse. This is the catastrophic, life-threatening stuff, yielding metal, crushing pillars, massive building sway, or structures physically overturning. We pad these with massive safety margins. On the other hand, we have the limit state of serviceability. This deals with the everyday comfort and function of the building. We're talking preventing things like bouncing floors, unsettling vibrations, or gradual corrosion. After all, it's not just about keeping the building up, it's about making sure it's actually pleasant and functional to be inside. Section 5. Engineering safety. Okay, so here is one of the most important numbers in structural engineering, 1.10. This is the partial safety factor applied to the basic yielding strength of structural steel. Think of it as an invisible mathematical buffer. Because humans manufacture steel, there will always be tiny imperfections or just slight manufacturing tolerances. By applying this factor, engineers artificially reduce the assumed strength of the steel in their calculations. Basically, they design the building assuming the steel is weaker than it actually is. That ensures a totally consistent, ironclad level of safety. But wait, they don't just pad the strength of the material. They also pad the loads the building is going to face. The structural code probabilistically combines multiple factors. The dead load, which is the permanent weight of the structure itself, the live load, like the unpredictable weight of people and furniture, and extreme forces like wind or earthquake loads. When you look at how they combine dead and live loads, engineers actually multiply the expected weight by a massive factor of 1.5. They are intentionally designing for the worst-case scenario, padding the numbers so heavily that the building is completely overprepared for literally anything the real world throws at it. And that brings us to the end of our journey. It completely changes how you view the world around you, doesn't it? Knowing that when you look at a skyline, you aren't just seeing static metal. You are witnessing a delicate, microscopic recipe of iron and carbon atoms, rigorously physically tested and governed by rigid, probabilistic mathematics. All of it working in perfect harmony around the clock to support the vibrant cities we live in. Thanks so much for joining me on this explainer, and as always, stay curious.